Dear students, in this module we will be deriving the eigenvalues of angular momentum operator. So after studying this module, you shall be able to find the eigenvalues of angular momentum operator. You will also be able to learn about the role of ladder operators, and you'll understand the relation between eigenvalues of angular momentum component Lz and total angular momentum operator L square. We have already discussed the significance of angular momentum operator in quantum mechanics in our earlier module. The theory of angular momentum in quantum mechanics is relevant in the context that angular momentum operator commutes with the Hamiltonian. That means the eigenfunction of angular momentum operator is also the eigenfunction of Hamiltonian, and it is for this reason we will be deriving the eigenvalues and eigenfunction of angular momentum operator. In quantum mechanics, angular momentum is of two types: orbital angular momentum denoted by L, capital L, and spin angular momentum denoted by capital S. We started with orbital angular momentum and we will be using the same over here as well. Orbital angular momentum is related to circular motion of an object. The Cartesian components of angular momentum operator are as follows: Lx caret, that is the angular momentum component in x direction, is equal to y caret pz caret minus z caret py caret, which is equivalent to minus iota h cross y del by del z minus z del by del y. Similarly, we have Ly component, that is the component in y direction, as z caret px caret minus x caret pz caret, which is equal to minus iota h cross z del by del x minus x del by del z. And likewise, we have the angular momentum component in z direction as Lz, which is equivalent to x caret py caret minus y caret px caret, which is equivalent to minus iota h cross x del by del y minus y del by del x. From the fundamental commutation property, we know that no two components of angular momentum operator commute, and they obey the following set of commutation relations. The commutator of Lx Ly is equal to iota h cross Lz. The commutator of Ly Lz is equivalent to iota h cross Lx, and the commutator of Lz Lx is equal to iota h cross Ly. But each of these components are known to commute with L square operator, that is the total angular momentum operator, which is given as Lx square plus Ly square plus Lz square. From here, we conclude that no two angular momentum components are compatible. Only the total angular momentum L square and any one component of angular momentum operator can share simultaneous eigenstates. With this brief review on angular momentum operator in quantum mechanics, we will be now deriving the eigenvalues of these angular momentum operators. For quantum mechanical problems involving angular momentum, the key operators of interest are Lz, that is the angular momentum component in z direction, and L square, which is the total angular momentum, as they commute. Now, the commutation relations of angular momentum operators are sufficient to deduce the eigenvalues of these operators without reference to the coordinate system. Also, it is important to note over here that one can use Lx operator or Ly operator in operation with L square instead of Lz operator. However, in this study, we have consistently used the component Lz in operation with L square. So, we will be using the same throughout the module. Now, with this, we will now look into another set of operators, that is ladder operators, which are used to obtain the eigenvalues of angular momentum. Ladder operators. In order to obtain the eigenvalues of angular momentum operator, a set of angular momentum operators are combined in the manner L plus, which is equal to Lx plus iota Ly, and L minus, which is equal to Lx minus iota Ly. Over here, L plus operator is referred to as raising or step up operator, and L minus operator is referred to as lowering or step down operator. Together, the operators L plus and L minus are called ladder operators, and this naming convention for these operators will be clear once we derive the eigenvalues of Lz and L square operators. Now, since total angular momentum, that is L square, and angular momentum component Lx commute, let us take y as the common eigenfunction of these operators. With this, the eigenvalue equation for the two components now become L square y equals to Cy, Lzy equals to By, where C and B are the eigenvalues in the respective expressions. Now, before deriving the eigenvalues of angular momentum operator Lz and L square, we will first look into some important ladder operator commutation relations which will be used later on. First is the commutation of L plus and Lz components of angular momentum, where the substitution of L plus operator modifies the expression to Lx plus iota Ly, Lz, which on simplification gives the expression minus iota h cross Ly minus h cross Lx, which is equivalent to minus h cross L plus. So that means the commutator of L plus Lz is minus h cross L plus. Further simplifying this commutation relation, we get the expression L plus Lz equals to Lz L plus minus h cross L plus. With this, we now move to the second commutation relation between L minus Lz. Substituting the value of L minus operator, we get the expression Lx minus iota Ly, Lz. Now, this commutation relation on simplification gives minus iota h cross Ly plus h cross Lx, which is equal to h cross L minus. That means the commutator of L minus Lz is h cross L minus. Again, simplifying the expression gives us the equation L minus Lz equals to Lz L minus plus h cross L minus. With this, the third commutation relation is of L square L plus, where substituting the value of L plus gives us the expression as commutation of L square Lx plus iota commutation of L square Ly. And since we know that total angular momentum operator L square commutes with each of the angular momentum components Lx, Ly and Lz, therefore the commutator of L square L plus becomes 0. Similarly, we derive the commutation relation of L square L minus, where on substituting the value of L minus, we get the expression L square Lx minus iota L square Ly. Again, since we know that the total angular momentum operator commutes individually with Lx and Ly, therefore again the commutator of L square L minus becomes 0. With this, we now move towards the derivation of eigenvalues of angular momentum component Lz. We already defined the eigenvalue equation for Lzy equals to By, where y is the eigenfunction and b refers to the eigenvalue. Now, operating on this equation with operator L plus, we get the expression as L plus Lzy equals to L plus By. We have already derived one commutation relation between L plus Lz, where the result has been obtained as L plus Lz is equal to Lz L plus minus h cross L plus. Substituting this result in the equation L plus Lzy equals to L plus By gives us the expression as Lz L plus minus h cross L plus y is equals to L plus By. Further, this can be rewritten as Lz L plus y equals to b plus h cross L plus y. Now, this equation indicates that the function L plus y is the eigenfunction of angular momentum component Lz with the eigenvalue as b plus h cross. This means that operating on the eigenfunction y with raising operator L plus converts y into another eigenfunction of Lz with eigenvalue higher by a factor of h cross. That means application of raising operator to the equation Lz L plus y equals to b plus h cross L plus y gives Lz L plus square y equals to b plus 2h L plus square y. Repeated application of raising operator gives the expression as Lz L plus to the power k into y equals to b plus k h cross L plus to the power k y, where k can take up value from 0 to the value defined. That means k can take up value 0, 1, 2, 3 and so on. Likewise, the operation of lowering operator L minus gives us the expression Lz L minus to the power ky equals to b minus k h cross L minus to the power k y, where again k can take up value 0, 1, 2 and so on. These expressions reveal that the application, or I can say the repeated application of raising and lowering operators on the eigenfunction y with eigenvalue b generates a ladder of eigenvalues which differ by a factor of h cross at each successive step. And it is for this reason that the operators L plus and L minus are called ladder operators, as their successive application creates a ladder of eigenvalues or eigenstates of Lz. It is also important to note over here that the application of L plus or L minus destroys the normalization of eigenfunction y. Now, after deriving the eigenvalues of angular momentum component Lz, we now come to the eigenvalues of total angular momentum, that is L square. We have already defined the eigenvalue equation for total angular momentum as L square y equals to Cy, where C denotes the eigenvalue of total angular momentum. Now, we know that total angular momentum commutes with the angular momentum component Lz, which means that the eigenfunctions of angular momentum component Lz are also the eigenfunctions of L square. Now, operating on the eigenvalue equation of total angular momentum with operator or raising operator L plus gives us the expression as L plus L square y equals to L plus Cy. We have already derived one commutation relation between L square and L plus, where we found that the commutator of L plus L square is equals to 0. Using this result in this equation, we can rewrite the equation as L square L plus y is equals to L plus Cy. Repeated application of a raising operator over here gives the result as L square L plus to the power ky equals to L plus to the power k Cy. And likewise, the operation of lowering operator L minus on the eigenvalue equation of total angular momentum gives us the expression L square L minus to the power k y equals to L minus to the power k Cy. Over here, we find that the expressions indicate that the eigenvalues of total angular momentum remain the same irrespective of repeated application of L plus and L minus operators. With this, we now come to the relationship between eigenvalues of angular momentum component Lz and total angular momentum L square. We have already derived the eigenvalue expression for total angular momentum and angular momentum component. The eigenvalues obtained for angular momentum component Lz are of the form Lz yk equals to bk yk, where k can take up value 0, 1, 2 and so on, and over here bk is equal to b plus minus k h cross, and yk refers to the operation of raising or lowering operator, that is L plus minus to the power k into y. Now, the eigenvalue obtained for total angular momentum follows the equation L square yk equals to cyk, where yk is equal to L plus minus to the power k y. Now, the question that might arise in your mind is that what is the range, what is the lower and upper limit for the set of eigenvalues of Lz, or do they extend indefinitely? Definitely, the set of eigenstates or values of Lz generated by ladder operators must be bounded. That is, the ladder cannot extend indefinitely. Now, let us see what is the limits or how the eigenstates of Lz operator are bounded. Now, operating on the eigenvalue equation of Lz component with Lz, we have Lz square yk equals to Lz bk yk, which becomes equals to bk square yk. Now, subtracting this equation from the eigenvalue equation of total angular momentum, we have the expression L square yk minus Lz square yk equals to cyk minus bk square yk. Now, the left hand side expression can be rewritten as L square minus Lz square equals to Lx square plus Ly square. So, we now have on the left hand side Lx square plus Ly square yk equals to c minus bk square yk. Now, the term on the left hand side, that is Lx square plus Ly square, is a non-negative term, which means that b is limited by the condition that c is greater than equal to bk square, or one can write that c to the power half or c under root is greater than equal to modulus bk, which means that the lower and upper limits of bk, that is the eigenvalues of angular momentum component Lz, are under root c greater than equal to modulus bk, which is greater than equal to minus under root c, where k can take up value 0, plus minus 1, plus minus 2 and so on. Now, let us now consider Bmax and Bmin as the largest and smallest eigenvalues of Lz operator modifies the eigenvalue equation of angular momentum component Lz as Lz Ymax equals to Bmax Ymax, Lz Ymin equals to Bmin Ymin. Now, operating on the Bmax equation with L plus operator gives us the expression L plus Lz Ymax equals to L plus Bmax Ymax. This further can be simplified as Lz L plus Ymax equals to Bmax plus h cross L plus Ymax. This eigenvalue has been obtained by application of raising operator, which has been found high times higher than Bmax, which is contradicting as we defined Bmax as the largest eigenvalue of Lz component. Now, the only possibility in this contradiction is that the function L plus Ymax vanish. That means L plus Ymax becomes equal to 0. Now, operating on this expression with lowering operator L minus gives us the expression L minus L plus Ymax equals to 0, where the multiplication of ladder operators L plus and L minus gives us the expression as Lx minus iota Ly into Lx plus iota Ly, which on simplification gives us the expression L square minus Lz square plus iota commutation Ly Lx. And with this, we obtain the final expression for multiplication of ladder operators as L minus L plus is equal to L square minus Lz square minus h cross Lz. With this, the expression now becomes L square minus Lz square minus h cross Lz Ymax equals to 0. Substituting the eigenvalue equation for L square and Lz, we get the expression as C minus B max square minus H cross B max Y max equals to 0. This indicates that C is equals to B max square plus H cross B max. On similar grounds, the lower limit is obtained as C equals to B min square minus H cross B min. Equating the two equations gives us the expression as B max square plus H cross within brackets B max plus B min minus B min square equals to 0. Now this becomes a quadratic equation which is solved for the unknown B max, and this gives us two roots for B max as minus B min, and the second is B min minus H cross. Since we said that B max is the maximum or the largest eigenvalue, so definitely this cannot be less than B min, because of which the second root B min minus H cross is rejected, and hence we are left with only one possibility, that is B max equals to minus B min. With this, the eigenvalues of angular momentum component Lz becomes Bk is equals to B plus minus Kh, where K is equals to 0, 1, 2 and so on. B max minus B min equals to Kh cross. Now substituting this expression, we get the equation as 2B max equals to Kh cross, which on further simplification gives the value of B max as Kh cross by 2, which becomes equals to Jh cross, where J is taken as K by 2 and K can take up value 0, plus 1, plus 2 and so on. So B max can have values 0, 1 by 2, 1, 3 by 2, 2 and so on. And likewise B min becomes equals to minus Kh cross by 2, which is equal to minus Jh cross. So in general, by virtue of ladder operators, there are an integral number of units between B max and B min, and the eigenvalue C of total angular momentum L square becomes equals to C is equals to J plus 1 H cross square, where J can take up value 0, 1 by 2, 1, 3 by 2, 2 and so on. Now substituting these expressions for eigenvalues of Lz and L square, we get the eigenvalue equation for the two as L square y equals to J plus 1 H square y, where J can take up value 0, 1 by 2, 1, 3 by 2, 2 and so on. And the other equation is of the form Lzy equals to Mj H cross y, where Mj can take up value from minus J to plus J. That means the range of eigenvalues of Lz is limited by J and minus J, which means a total of 2J plus 1 eigenstates are possible for angular momentum component Lz. Now with this, we summarize whatever we have done in this module. We derived the eigenvalues of angular momentum component Lz and angular momentum operator L square. The eigenvalues of Lz are either integers or half integers, that is, they differ by integral steps. The eigenvalue equation for this is of the form Lzy equals to By, where B is the eigenvalue which is taken as Kh cross by 2 equals to Jh cross, where J is equals to K by 2 and K can take up value 0, plus minus 1, plus minus 2 and so on. That means Ljy becomes equal to Mjhy, where M is equals to minus J to plus J. Now the eigenvalues of Lz are bounded in such a manner that C, that is the eigenvalue of total angular momentum, is greater than equal to Bk square, that is the eigenvalue of angular momentum component Lz. Lastly, the eigenvalues of total angular momentum operator L square is of the form L square y equals to Cy, where C is the eigenvalue, and the expression becomes L square y equals to J plus 1 H cross square y, where J can take up value as 0, 1 by 2, 1, 3 by 2, 2. With this, we have defined the eigenvalues of angular momentum operator using ladder operators. And then in the next module, we will be taking up the derivation of eigenfunction of angular momentum operator.